Hi, welcome. Good night for everyone who is in the same time zone as me, and well, good morning for any other time zones. I think. Well, of course, that's not how it works, but I just like to say good night or good morning. So we have a comment here about Fluffy Blue saying hello, everyone. Hello. So I'm so glad to be here for this last session of um, I don't know why I call this the data in education part four. I'm just make a terrible mistake. Um, Let me change this really quickly. I just realized that. I completely don't know why. Um, Give me a second. I hope I still can change this. Neural networks using MATLAB. Yeah, data in education was the one from Carrie, I think. Okay, yeah, it's changed now. So I'm so sorry if any of you joined thinking this was the um, mm, what data in education. I think was the name. Yeah. So sorry about that. Yeah, this is the fourth part of neural networks using MATLAB. So in the first part, we check some basic theory about neural networks at all, a little bit of history, how are they built, like the principal parts, um, input, weights, bias, transfer function, um, how we connect them, like architectures, layers. What else? We talked about the recipe, well, how these can be considered recipes, like in a metaphor of cooking, and how you can then or now with some experience create your own recipes, right? And we talk about very famous recipes as the Hamming network, perceptron, and now we're going to talk about Adeline. In Hamming Network, we explore how we can also have neural networks independent from artificial intelligence, because, yes, these are very interlinked topics, but they can also be separated. Um, but artificial intelligence actually gives more, how to say this, power to neural networks by enabling them to learn. Um, yeah, that's how I will declare that or explain it. And for example, in Hamming network, we make all calculus ourselves. We follow the recipe, and then we apply no learning. We actually give all the network the parameters for making classifications correctly, right? So for past session, part three, in the perceptron, or we also introduced how we could um, make these manual calculus to make the network able to classify correctly by introducing something called the decision boundary, and how we can calculate or get the weight matrix and the bias vector graphically. But we also state that doing that for more than two or three dimensions in a real case scenario could that be possible. So we introduced the learning rule for the perception, right? So that's a real very quick recap of previous sessions. If you missed them, go check them out. There's the recordings on YouTube and Twitch, and let's start with this part four to check outline. So let me start sharing my screen. Also, I want to tell you that we probably be ending this session a little bit sooner because I also have a next session coming up. It's just a Gartic phone mini event, but I probably will need 5-10 minutes to prepare that. So um, that's why I also wanted to go straight to the topic here. Okay. Uh, we will be checking chapter 10 of neural network designs. I shared this book with you, but also I can share it again for those who missed previous sessions. So give me a second. Give me a second, and I'll post it here. Yeah, right. Here it is. And before I forget, go check yourselves into this event to receive the community points, right? So previously we checked chapter 1, 2, 3, and 4, I think. No, yeah, 4 for the perception, of course. We checked 4 chapters in the previous sessions, and in this one now, we are going to check, we're going to skip a little bit of chapter 5, 6, 7, 8, and 9. You can take a look to the content of it. For example, yeah, we checked the introduction. Chapter 1 was really short, neural network model and architectures. Chapter 2, we checked the example, the illustrative example for becoming network and perceptron, the fruit classifier. For chapter 4, we checked the perceptron learning rule. We're skipping signal and wake vector spaces. This is like a little recap of mathematical theory for matrix operations. Linear transformations for neural networks can be handy if you want to have more math background. 7, supervised heavy learning. These also I'm going to skip it because I want to take a look to another type of learning, which is the Woodrow Huff, which is the chapter 10, performance, surface, and optimum point. This is another recap for you if you don't have much idea on mathematic concepts. Taylor series, minimal, quadratic functions, etc. Performance optimizations. But yeah, taking with chapter 10, Woodrow Huff learning. So let's go there, right? Here, we introduced previously the performance learning foundation, um, and we also introduced the perceptron learning rule, right? So a little bit of concept of these. Well, not concept. Sorry, a little bit of context. Sorry, for this network. It's that the creator, what's it's around here, Bernard Guido, began working in neural networks around the same time Perceptron was released. But when they released the learning rule in the same time Whitrow released with one of his students the Adeline adaptive linear neural network, and its learning rule, which they call least mean square algorithm. This learning rule, again, we can call it learning rule. The one for the perception was the perception learning rule. This one has a more interesting name, the least mean square algorithm, but still it's a learning rule. Also, they have another one which is the delta delta learning, something like that. Let me check my notes on here. Uh, yeah, delta rule. Delta rule, Woodrow Huff algorithm, least mean square. They can be very names for this. So, well, a way to call this is LMS. Don't confuse it with these initials because, again, LMS can sound very different depending on the context, but least mean square, let's just call it by its full name. It's the name of this learning rule, right? The outline network, it's very, very similar to the perception. Actually, this is the draft of it. If you put a lot of attention, the only thing it changes with the perception, it's the transfer function. In transfer function, I mentioned perceptron had to be Harlim or Harlim symmetrical, meaning that we have a binary output out of perceptron, right? This Adeline network has a linear output since, again, I mentioned this can be used not only for classifying but for predicting, making regressions or making yeah, or trying to predict numbers that it's in not in the training set, right? Um, so that's why the the transfer function, sorry, it's going to be linear. In this case, it's purely, but it can be any other linear function. Okay, returning here, we were talking about these very, very similar. Both line and the perception then suffers from the same limitation, and I talked to you about this, which is we have to be linear separable problems. They can only solve linear separable problems. However, Adeline, despite perception, it's a little bit more powerful due to two reasons. One, the algorithm, the training algorithm. Um, Actually, one of you, if I remember well, it was Oib, make a great question about this, how we can know if it's well trained, right? And I'm going to take a pause here to remember perception results. In our results, we talked and we checked the results for this, for example, perceptron training rule that for this little point here, the yellow point, it's really close to the line. For the values here, they classify them correctly, yes. But, however, distance from these points to the lines, to the decision boundaries, can be random. I mean, if I run this again, and I will do it, the result, okay, let me change my path. Sorry, I was working in the other path. The results here, uh, what? Oh, here. For example, decision boundary here changed a lot, but a lot. So now there's a lot of space here for this purple class in which all the dots or all the points in this area are going to be classified as this class. And same with the yellow. Yellow has a little less surface in which these points are going to be classified as the yellow class. Why is that? I mentioned you that learning rule in perception, what it does is that it takes the decision boundary and starts rotating them until, well, not until, and checking if the resulting classification it's close to the result we want, to the target. Because again, we are talking about supervised learning here. And if it is, it moves the line towards the direction of the classification. If it is not, it move it the other way. But it stops just right when we hit the desired classification. So the training points are really close in some cases to the decision boundary. What makes the Adeline uh, network more powerful than the perception, it's that the least mean square algorithm does not try to just complete the training and that's it. Um, During the nature of the list of the mean square, the the decision boundary it's moved as far as it can of the. Let me change the layout. Sorry, I just realized this so you can see better. um, it moves as far as it can of the training points. So it will try to be in the middle of all the data, of all the training points. So there will be more room for all of the classes to be classified correct. And we have the ability then to reduce training sets. Also, sorry. Also, one of the reasons it is more powerful again, it's because not only can classify, but it can be predictive. Um, yeah, so that's the introduction here on Adeline. The perception is guaranteed to converge, blah blah blah. Algorithm minimize mean square error, and therefore tries to move decision boundary as far of the training patterns as possible. This is the interesting thing to talk about, right? The least mean square algorithm has found more practical use than the perceptual relearning rule. This is especially true in the area of digital signals. And a fun fact here is they mention in the book that because of this, because of the popularity of this algorithm and the lack of success of adapting the algorithm to multiple layer networks, we already started working on neural networks in the early 60s and began working full time of signal processing. Then resumed to its works in the late 80s and began the research of neural networks adapted to control using temporary backpropagation. Backpropagation is another very, very interesting topic, but we are not going to be able to cover this since we are getting a little bit far of that processing and entering more in the world of AI, right? So, again, uh, we could, but hey, everybody, it's going to need time to process all of this information. And maybe for the next Global Hack Week about artificial intelligence or data, we can talk about more complex stuff like this, right? For the moment, we just have beginners week coming up in January. It's a great, great way to start the year. If you are feeling kind of intimidating with all this information, with all this heavy stuff, and want to explore more beginner friendly things, Global Hack Week, Beginners Week, it's going to be a very, very, very week for you. I mean, in all weeks, we try to do complicated sessions and, well, more complex session, I would say, and more beginner friendly sessions. But this week is especially for beginners. So we probably will be dealing with introductions like introduction to Python, introduction to this. Actually, again, this is an introduction to neural networks. So it will be great that if you missed any of the previous parts or any of the previous sessions, you take a look at them, come back. Well, don't leave now. I mean, come back and rewatch this session, and we will be ready next time for backpropagation, for example, or applying these or creating neural networks with many, many layers or many, many neurons at a time, right? So let's get started with outline now. Formal definition. Again, the structure is this. We only change in comparison of a perception the output, meaning changing the transfer function. So we will be having linear output, not a single binary decision here, and it's going to be same. Same formula. Take a look at what we were mentioning here. For example, with purling, if you remember at having network, one of the layers had the same function, and I was mentioning that it doesn't matter that you see something like this, you can't forget you have a transfer function. In this case, what enters gets out, no transformation, so that's why they made it obviously like multiplying to one, but don't forget you have a transfer function. It's very important, and you cannot have a neural network without having a transfer function. Now recall what this is. We have the weight matrix vector, the input vector plus the bias, right? In this simplicity example, we're going to consider um, an adeline neuron without a bias. Why is that? Because of computational effort. And we can discuss more about this, but for the moment, again, I will need you to trust me. We are going to make bias zero in this case, and it's not the first time. For example, again, one of the layers of, and in the recurrent layer for Hamming, we also made bias zero, right? So let's do that again. To simplify the discussion, let's consider a single headline with two inputs. The diagram for this network is shown here. We have the two inputs. Here in the book, we will still consider the bias. For our example, we're not going to consider bias, or we are going to make it zero, same as the transfer function. It's not like there is no bias, right? There is no transfer function. Yeah, it is, but we're adding zero and we are multiplying to one, right? Um, and that's it. Here we also have the decision boundary, right? But in this case, since we don't have an binary output, the thing that it's going to happen is that the predictions or the results here, A, in the gray area, they are going to be bigger than zero. In the white area, in the rest, they are going to be less than zero. They are going to be negative, right? So, in this case, sorry, um, we can contain the outputs can contain multiple values. It can be 0, 0.1, 0.2, 0. Again, it's a linear output, and the results here are just going to be, for example, for classification, that the one of the categories is going to be bigger than zero, and the other category is going to be less than zero. So then again, in the inspecting the result and getting the insights of it, we need to make these considerations, right? Then, and again, sorry for this. It's going to be a very theoretical explanation. I'm going to skip a little bit of the things that are explained here. But if you want, and if you enjoy, because many people do it, mathematical descriptions and demonstrations, you can always watch this part of the book, right? I just want you to know some very important concepts, and then we are going to take them to the code, right? That's my purpose here. Mean square error. Uh, Here we are going to follow the same supervised learning method. We have to have inputs and targets in the same way. This is going to be the algorithm. So uh, they define an input vector, right? Um, well, the the simplified available number parameters. Well, okay, this is not the input vector. Sorry, this is like the body cell vector. We can think of it, and we have the weights and the bias. Right. In this case, the weight for this example, as they mentioned, it is two input, one neuron network, Adeline network. So this is going to be just one vector, right? Remember that. The size of W, it depends of the number of neurons. Since it is only one, it's going to be a vector. And bias again, it's a scalar in this case. Similar, we have the input vector, but in this case, we add a 1 as the bias that it's going to be entering the network, right? So we used to define the output as this, W, P plus B, but with these considerations, we can rewrite it just as X transpose theta, right? The least point, we are just making some adjustments on how we represent the equation, but it's the same, right? No problem to do that. Now, this is how we define the mean square error. F of x, it's equal to e um, to the second um, squared, meaning e the difference between the target and the classification. Remember that we already checked that, very similar in the perception learning rule. The difference here is we are squaring this error. Well, the expectation is taking over the sets of input target pairs. Here we use the notation E with squared brackets to denotate the expected value, right? So then we apply and we do a little bit of math. And this is why it was important to mention the previous chapters, especially 5 and 6, because here we apply some identities. For example, this one that tell us what which insights we can get from these matrix operations. Thankfully, the book explains it to us. Here, the vector h gives the cross relation, and this is h. Sorry, the h is defined as the target times the vector theta. It's the cross relation between the input vector and its associated target. R is the input correlation matrix. Diagonal elements of this matrix are equal to the mean square values of the elements of the input vectors. Again, don't worry if you feel this is too much maths. This is just for the scientifics to to get to the result. But again, if at some point you want to create your own networks, make your own designs and stuff, yeah, you need to make and be sure to put a lot of attention here. And I'm sure that's all that we want, right? At least it's one of the things I want. Then they tell us to take a look to this form because if you notice, it's very similar to compared to what the general form of the quadratic functions are. If you change the values, of course, you can have x squared and two x squared and x, right? Um, so the represented form have these same um, definition. So we can see that we with the mean square from the index of the other network, it's a quadratic function where d it's equal to minus 2h and a it's equal to 2r. Okay, so again, if maths does not fit for you, like what just happened, just trust the authors, trust me, and we can follow with the results, right? Um, okay, I just need to make a quick pause. Sorry. Meanwhile, you can take a look and read the explanation of how we discover these functions, right? I'll be back. And they mentioned chapter 4, for example. That's why it is important to have all of that background of those chapters. But the meat, like the juicy thing, it's in this one, right? I'll be back in a second. Hey, sorry, I'm back. I just needed some water. Um, okay, where were we? Yeah, we were checking a look to how we get to the final formula we want to apply, right? Like good engineers. This is a very important result that comes from chapter 8. So take a look to that. Now locate the stationary point of the performance index. From our previous discussion of quadratic functions, we know this gradient of the function. We apply the gradient and we have d plus ax, meaning with the previous values we get that it's minus 2h plus 2rx. So the stationary point of the function can be found by the setting gradient equal to 0, meaning that the corresponding matrix has a positive definite, a definite positive in the unique stationary point given by x equal r minus 1, well, uh, elevated to minus 1 h. Um, and this is just for explaining what the least mean square is, well, the mean square error is. Now, once we have this background of the maths needed, we can start developing the algorithm, um, which is here, the least mean square algorithm, right? And it's the same. Now that we have analyzed our performance index, the next step is to design the algorithm to locate the minimum point of it. If we could calculate the statistical quantities h and r, we can find the minimum point directly. And again, they agree that calculating this inverse of r, given here, could not be the best anytime. And again, there's always a beautiful math way for doing anything, but the problem here is that equations need to be well defined, and that's work for mathematicians. But here, thankfully, we have algorithms to help us resolve this, and they suggest using the steepest descent algorithm with the gradient calculating form of the equation, which is this one here, to solve the uh, least mean square, right? For this reason, we use this approximate step descent algorithm in which we use the estimated gradient. Yeah. Um, Again, in general whole, it is not desirable or convenient to calculate h and r like anytime, right? So let's start applying the algorithm, and we see again the mean square. It's here. The mean square error. Sorry, I need to specify now that it's applied for the error by the formula fx, where the expectation of the square error has been replaced by the square error in an iteration k, right? Then at each iteration, we have a gradient estimate of the form this. So then now needs to apply derivatives referred to the stochastic gradient. In this way, we apply the derivatives respect of the weights while the iteration is still happening. The elements of the derivative, and sorry, don't worry, again, you won't have to derivate these in code. Then just need to follow to see the output in a general matter form, which is the formula we're going to apply. So we apply the derivatives and we see that when we evaluate the partial derivative of the error with respect of the derivatives of the weight, we have the result given by the input of the align network. This is the element of the input vector of the kth interaction and can be simplified in a way that it can be considered just as the minus one, right? In a very similar way, we can obtain the final element of the um, gradient of the error like this, and the gradient of the error about the weights, it's going to be minus the input vector. Again, for the bias, minus one, and for the input vector, sorry, for the weight, it's going to be minus the input vectors. So note that the input vector k and 1 are the elements of the input vector zeta that we previously defined. So the gradient of the squared error at any iteration k can be written as follows. So now we can see the beauty of approximating because the mean squared by error by the single error at iteration k, um, as in this previous formula we declare here, it's to calculate the approximate gradient we need to multiply the error anytime till this input. Um, Substituting elements and doing the appropriate maths, we get that these can be written in the form of W, or the weight matrix that we are going to update. It's going to be the previous weight value plus a 2 alpha. In this case, we're going to call this delta times the error of the previous value times the input of the previous value, right? And same with the bias. So these two looks very similar to the perceptron learning rule, except that in this point we now introduce this alpha, and what this alpha is. Well, the preceding results can be modified to handle the case where we have multiple outputs, therefore multiple neurons. Yeah, because this was proved just for the two input example, but if we make this to the correct notation, this is the vector, the vector, vector, and vector, and they also make emphasis on that. Note that the error and the bias are vectors now, right? Because we were used to working with bias in a scalar way, right? To make sure you are aware of that. These last two equations make up the least mean square algorithm. So these are the least mean square algorithm. This is also referred as the delta rule. That's why I know this can be confusing. Actually, I'm still confused. I don't know why this it's called the delta rule, but we use the don't worry. I'm confused too. But let's call this the delta rule. Um, we draw half learning rule, the LMS algorithm, etc. Um, but yeah, now that's it. They proved and make an analysis of convergence, but we are not going to take a look of this. Uh, we just needed the algorithm, and they mentioned also the applications of these, for example, the adaptive filtering, because we also mentioned that Adeline was, well, not Adeline indeed, but LMS was very widely used in signal processing. Um, Woodrow dedicated a lot of time in his life to this field, so there are some applications here about that. Adaptive noise cancellation, for example. Actually, I don't know. I don't want to lie again, but last time I checked, I read a source in which they were saying like Adeline was used nowadays for making phone calls, like for connecting and yeah, for filtering doing the filtering in phone calls. And also here for noise cancellation, that's still a great way to do this. So despite, for example, again, perception, that it is a great algorithm and network to study neural networks, it is not widely used. Adeline, it's very common use neural network right now nowadays. So that's why I wanted to end the series at least this, let's call it um, first season of four series with a real world scenario, right? So I have this on code. So now let's jump to MATLAB to check how we translate this LMS algorithm, least mean square algorithm, right? Hey, we have a comment here about Malik. Hi. Sorry, I was using. Sorry, I was busy. Sorry, making my portfolio. That's very nice. So, what were you building? Did you complete yet all challenges for this global head week? And how about the rest? How about you, Fluffy Blue Topaz? Hmm, nice. So, I hope you replied. Let me jump back to Adeline Network. Same, you know how I like this creating the class definition for the networks. We have same weight bias, the transfer function. In this case, we are just receiving and we are going just to use one one neuron Adeline. Because you remember, for example, for perceptron, I created number of neurons depending on how many classes I wanted to classify. In this case, it is not necessary. In this case, I'm just going to use one neuron and just set the size depending on the input size, right? The bias it's going to be zero, again for simplicity reasons, and the transfer function is going to be purling. If you want to see the definition of purling, here it is. The transfer function. No, sorry, I'm in the wrong. I'm still in perception. This Adeline transfer function. Yeah, whatever it enters, it goes out. Very simple transfer function, right? uh, so I know it can be silly, but it is important to have it in mind just as the theory concept. Then classification, it's done the same. Net input, or n, it's going to be weights times times the p input plus the bias. In this case, again, I could delete this because bias is going to be zero, but I won't because in the future this can change. This transfer function, it's the same as not putting anything, like just directly hitting output, it's equal to net input. I know it, but again, I won't change it because it is important to have it in mind that we are using a transfer function and it can be building and maybe it can be changed in the future. Function to train. In this case, we also receive the prototypes, the max epochs, and we have the delta, right? Remember, it is very important for LMS to have a delta. Train Erlang using this. We also train until we know all results are correct, or until we hit the max epochs. If we hit the max epochs, we say A, we stop because max epochs were reached. Else, we say training is complete and it is successfully, right? Actually, here I kind of do a copy of the perceptron, but there are some changes that need to be done in the Adeline network. work, and you will help me doing these changes here live, right? Hey, wow, look at this. This is a surprise. 404 not found 19. I'm alive. That's a really, really great thing to have. Um, and also, I made a guild in MLH. One shout out to Web Wizards, please. Amazing. Oh yeah, I saw that you sent me a message about that. Sorry, I haven't had the chance to reply. I was preparing things for this stream, but hey, after this, I have the Gartic phone mini event. So why don't we discuss that there, right? Um, Also, all here are invited to that, of course. So yeah, returning to the code. Um, what I was saying, classify function, it's correct, so I can collapse it for the moment. Training, we can make some changes here on training, but for the moment, I want you to take a look. Like this is very simple. This is very similar to what we had on perception, but the updating of the weight and the bias is where it changed. Now we define the error as the target minus the classification. This difference it's going to be multiplied to delta to 2, and that's it. These little changes actually make a huge difference, and this it's the how to say this, like the result. Yeah, well, it is not like it is the result of all these development development, sorry, of the functions here, like how we prove this is correct, how we prove this is the same as applying the square mean and doing reading the CD, the descendant, and the all of those things, like with just this simple elegant approximation. Yeah, we have to specify this is approximation. um, we coded all of that math hard work, right? Else, we have like the log of progress, the plotting of the results, and then we check correction. Actually, this is one we need to change. Yeah, this is the one we need to change. This correct. Check if classifications are correct. It is not like we wanted. So I probably need to correct this. And the plotting too, I probably need to correct it because there are some difference from the um, perception. But with this, I created. Remember the orange and apple classifier? Well, we can set the same. Again, we define the prototype vector, we define the target, we made it dictionary, an object. I don't know. It depends in which language you're talking. I'm talking JavaScript, so this is going to be an object. Actually, in MATLAB, I'm not sure what this is. I'm not sure how these are called. Good question, though. Okay, it doesn't matter. Um, yeah, the prototype for the Apple. Sorry, I was thinking just another things. The target for the Apple. So orange needs to be classified at -1. Apple needs to be classified as 1. What else? Yeah, the the dictionary same here, or the object for the Apple. Prototypes are declared here. Analyze parameters, align parameters. Sorry, the input size is going to be the size of the first vector. Here, take a look to the max epochs. In perceptron, Yeah, we had like 100 epochs, and actually we just needed like two or three. In the worst cases, I saw like 100. But if sorry, I saw like seven or nine. But 100 was a lot, and 100 meant that um, you probably won't. You probably were doing something wrong. In this case, yeah, Adeline, it's more powerful, but that also means it needs more computational power, obviously for better results. Uh, let's take a look to how it looks in 100, and then you will see why I change it to 1,000. Then we create the Adeline network. We just pass as parameters the input size to this Adeline network. We create an instance that we set this instance that has Adeline to train using the prototypes, the max epochs we define, and the delta. For this training, actually, these max epochs, now I think of it, should be also here on the training. Yeah, this makes more sense. Okay, don't worry. Training, we set stop code, numbers of retries. In this case, I'm going just to add one number of retry. I mean, if it does not complete in just one run, then don't run it again. Delta. Oof, why delta? Why choose this value? I'm going to show you something. Analysis of convergence. Remember what we declare on the first part when we were defining the mean square, not the algorithm, just the this mean square. Well, sorry, let me read some comments here. Everyone's happy using TensorFlow until you learn to learn the calculus behind it. Yeah. Again, I don't know in which session I mentioned this because um, there's a difference and a really big difference between the developers that he applies this just directly using TensorFlow and PyTorch, and it's just like okay, yeah, it works. I don't know why, but it works. And the ones that actually know this, and you start getting difference when the library doesn't work, like when you don't get your expected output. Then you can again start trying, and at some point, if you're lucky, well, congratulations, you achieve it. But having the ability to knowing what's happening behind it and saying like, okay, I know why it's not working. I think it has more value than sometimes even that saying I know why it's working. But yeah, having the ability to that, knowing why it's not working, it's a big thing, and I wanted to share that with you. um, Amazed to see it. Welcome back. Wow. One pray for Alberto to get rid of his last semester fastly. Oh yeah, thank you for that, because yes, I am super. I'm super tired I don't know why. Sorry, I don't know how this is in English university, but not like university in general. Not like I'm not tired of the learning. I'm just tired of my engineering course. I want to get to the master, so I want to get to the next level. But right now, uh, tired. Yeah. um, yeah, so again, it's not that I'm sick of the university as an institution. I just want to I just want, sorry, to get quickly, yeah, to the next level. But now. Like I need to finish before going to the masters, like the major. So that's the thing here. But yeah, thanks for the comment. Um, well, returning to this, why I got the 0.2 for the delta. Hmm. We described the uh, least mean square, um, and now we need to find a thing called the stability, um, which can be described as the range of values in which the training, we are between codes, sure, it will converge to a value, and it will converge to the desired classification, right, or the desired weights and bias values. So, same as previous, we could do it calculating a lot of stuff. Here, for example, they mentioned the expected value of the weight vector will converge to this formula. So in this case, uh, this is substituted by the formula we applied due to a lot of approximations. But here, now we take the expectation of both sides. We substitute the error for this given formula. We substitute the zeta and x transpose, and at the end, what we have, it's this stability where we have to stability range, where we have to apply some things called the eigenvalues of R. The eigenvalues, it's a concept that you will commonly hear when you do control stuff in control theory, of course. um, and this, what it will tell us, it's in which values of this lambda, the delta, it's going to work, and it's going to give us the converged. Well, it's going to converge into results. Again, this can be done manually. There's a chapter in which they explain this. But even here, for example, when we do it for the um, fruit classifier example of the apple and the orange, then we start substituting values and stuff. We get R, we calculate it here. Also, another thing that they have important here, it's that we declare and we um, start with the intuition that for both we are going to start with a symmetrical distribution of the weights, like here. If we assume that the input vectors are generated randomly with equal probability, we can compute. We can, if we don't assume this, we cannot. We can compute the correlation matrix. Once we have this correlation matrix, which is R, the eigenvalues for R are these ones. How you get these eigenvalues? Actually, MATLAB has a built-in function for that. Thanks, MATLAB. But if not, there are formulas. Don't worry, you can always Google it. And these give us the maximum stable learning rate, which is 0.5. So delta has to be less than that. What happens if we go over that? Well, take a look yourself. Let's just put 0.7, for example. We run this, and the results are one they are bad. This is like nonsense. This is a very 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 small number. Um, Another thing, if I do this more times, this probably it's just going to be like uh, yeah, not a number. You know, this won't converge. So let's return these to the previous values. I have 100 and 02, and that's the explanation on that, and that's the explanation on delta. But hey, Alberto, I thought we didn't have to calculate anything. Like, why are you telling me now to calculate? Well, again, this is explained here. To be considered, we will pick 0.2, not at in practical applications. It might not be practical to calculate R, right? Yeah. So delta could be selected by trial and error, and well, that that's it. That's how you can get your delta, trial and error. Other techniques for choosing delta are given in a reference of the book. You can always go and check them, but again, it's applying math, so be aware of that. Um, so now they develop the exercise here manually, blah blah blah. But of course, we know that the result we want it's P1 to be classified as -1 and P2 to be classified as 1, right? So I will just run it. It completed at 100 epochs. It tells me it starts the training stopped, sorry, with the maximum epochs reached, the value of the weights, the value of the bias, and what? We have the correct result. So what does training stop means? And this is why I mentioned you that this consideration here was wrong. The one of correct the correct method, because actually um, well the thing is that of course we classify correct, but what we probably want is to have the decision boundary just in the middle between these 2 points. So what was happening here is that this decision boundary it is not properly in where it should be. Um, so what happens if we increase the max number of epochs? Let's increase it to 100. Okay, again, classification it's done correctly, but the decision boundary is not where it should be. At least for what we should expect of the LMS algorithm. Let's try increasing the retries, because all this time the algorithm was running out of max epochs because it completed all. Uh, Values were changing. That's normal. So let's try increasing that number. It took some more time, but the decision boundary is still it is not where we want it. However, I want you to take a look that the classes, the prototypes are classified just as they should. P2 is 1, and P2, sorry, P2 is 1, and P1 it's minus 1. What is impressive about this? It's that, remember, the output of this, it's linear. So we could have any number, any number. For example, this one, this vector that it's not under the training set. This is new. The network haven't seen before, haven't seen it yet. Didn't had 1,000 of, well, 3,000 of these values. It is new, and it is classified as 1.5681. This is 1, this is 1, and the thing here is we are trying to make a graph of two dimension of a three-dimension vector, but there inside it's another point, well, another level, right? And the point is we are for sure that the classification it's good, meaning the same that we mentioned on our consideration, that it's the values in the gray area, the ones that are in the side where the matrix vector points, are going to be greater than zero, and the ones in the other area, they are going to be less than zero. Again, what is impressive is that these two are considered the these two are considered and classified, and the value is exactly what we wanted. Let's try just this 10 bucks. I'm just curious about this. Yeah, for example, in this case, it is very interesting that the prototype one was classified correctly, like in terms of it should be a negative one, but the linear output does not tell us exactly the value we wanted, the target we wanted. So yeah, that's interesting. The training required a little bit more. There's a sweet spot, I'm sure, between 100 and 1,000, or even maybe 1,000. Sorry, yeah, 1,000 is too much. The 100 could be great for this specific case. But yeah, the results are incredible. Well, at least that's what I think. Let's see some of the examples of the withdraw learning rule, the delta learning and stuff of the chapter. I mean, adaptive noise. Well, this is another section. Echo cancellation. There's another application where you can use this. The summary of the results. The applications, blah blah blah. Okay, yeah, the solved problems, right? Because obviously we want to solve. Um, these ones for the filter, so we're not considering these. Let's try. Suppose that we want to design an aligned network to distinguish between various categories of input vectors. Let us first try the categories list below. Category 1, it's going to be for this, and category 2, it's going to be for this. Can an adeline network be designed to make such a distinction? Well, how do you answer this? The correct answer is that we need to check first of all if this is linear separable problem. If it is not, then adeline won't be the result. Well, won't be able to give us a result for this. That's the main thing. So let's plot them. The input vectors are plotted here. So the blue line in this figure, it's a decision boundary that separates the two categories successfully. Since they are linear separable, a line network will do the job. So nice. We agree on that, right? We already knew because we put attention to Alberto's session. If the answer of the part one is yes, what set of weight and bias might be used? So why don't we run our previous code and discover what set of weight and bias the output was giving us? I'm going to update this in another code, main script. This is going to be uh, P10 to 2. And this is not for recognition, this is another thing. Um, category 1, category 2, 1, 1, minus 1, minus 1. Minus 1, comma, minus 1. And yeah, these two are going to be for this PT1, PT2, it's going to be PT2, T1. This is going to be category 1. Oh, what? Okay, nice. Now category 2. It's 3 here, 3 here, and what were the values? 2 and 2. And this is going to be for category 2, the P, T, 3. It's going to be P2, P3, sorry, comma, T3. Nice. Prototypes, I just need to add the P3. And what else? Okay, I think that's all. Input size is automatically calculated. The use of this isn't necessary. Okay, I don't care. What else? Blah blah blah. Okay, let's call this test 2. We're going to replace these. Just that. Because this one we want to continue them as test 1. Yeah, let's try PT1, PT2, and PT3. Nice. So let's run this. Okay, that's a problem. Dimensions of arrays being concatenated are not consistent. What? Why not? 1 1 1 1 1 1 1 1 1 one 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 51 53 P3 T3. Hmm. Okay, I may be doing this wrong. Yeah, yeah. Sorry, this was um, semicolon instead of comma. But yeah, let's run this now. Oops, another thing. Uh, so if this is happening, it's because something here it's wrong, not because of the line uh, network. It's wrong, except that this is untrained, this is unclassified. Yeah, no, no. This is not wrong in the other line network. This is wrong here. Let's just change some parameters. Mm, 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 mm. Again, I have a question here. Let me check what I might be doing wrong. One T T1 P1 PT1. Those four are 1x cells. Prototype is 3x1 cell. Um, Stove code still 0. Delta it's 3. The A does not appear here. I have a number of max epochs. Hmm. Don't know why I might be doing wrong here. Delta times the bias. Train. Classify. Okay, let me do something here just to check really quick. I'm going to delete this. Does the no? Yeah, this is the same. No problem. Oh no. Oh no, yeah, but the problem was here. But it is the same, like okay, yeah. Um, come on, see that. Come on, see that. Oh, no, I didn't want it to make that. Nice. Okay, yeah. The problem here is I might be running different sizes of matrix, but oh yeah, I can. This is semicolon. My God. Uh, yeah, my bad. Sorry. We have to be cautious about that. Uh, okay, nice. I'm just curious why decision boundary is there if these two were classified as same class. Actually, it looks very similar. Yeah, the only problem is decision boundary where it's being painted. Let's run this again. Okay, yeah, maybe decision boundary it's misprinted here, but the classification it's legit. I can tell. Um, yeah, let's try with a new value just to make sure of it. For example, 0.5, 0.5 should be classified same as red. That is that is positive. No, positive. Yeah, that's another problem. Weight matrix. Actually, this is too small, so maybe I need to start playing with these values. Let me check. Okay, yeah, it's positive, but um, you see, test and try your delta values, and let's increase the number of epoch first. Okay, this does not converge to anything, so probably we are applying bad delta. Now, the thing here is that I don't see value in logging this the number of epochs. At least not one. Let's make it every 100 epochs, so I cannot see all of these noisy blocks here. So yeah, no values and weights. Let's try increasing the delta. Again, no good. Let's try also changing the max epochs to 5, and let's decrease now delta to 0.1. Okay, now this is giving us something. Still, I don't see that this is being classified correctly. Um, P1 and P2 should be the same. That's negative. But P2, this one, it's being classified as sorry, this one it's being classified as positive. So let's reduce a little bit more the delta. Okay, a very small delta in this case. Now let's give more chances uh, um, for the max epochs to the algorithm to run. Okay, no, maybe we need even a smaller delta. Let's make this too much smaller and return to 1,000. Okay, now decision boundary it's where it should be, and all classifications here looks to be good. Exactly. Now let's make one that it's supposed to be classified as positive, which is 2 2, for example. Well, 2 2 is the prototype right now. Let's do it 1.52. Okay, nice, positive. Oh, wow, what happened with our decision boundary? This is not what we wanted. Okay, interesting. Okay, maybe even smaller? Yeah, 1,000 can be great. No, no, this time it affected. So again, test and try. Maybe that was a problem. It was too small. Okay, a little bit better. 0.05. Do I try that? I cannot remember. Okay, yeah, I think I tried and it wasn't working. Okay, that's fine. One time it worked. Second time it barely worked. Third time it worked. Okay, eh, fair enough. So, um, weight values. They're too small. 0.47, 0.11, 0.6, 0.06, 0.35, 0.25. Actually, this is the one I like the most. So this is the one we are going to propose to reply to this exercise. The question was, if the answer of the part was yes, what's the set of weight and bias might we use? The decision boundary passes through the point uh, 3 and 3. We know these points might be intercept minus b, and this minus b in weight 1 1 and weight 1 2. This the solution, it's bias equals 3, weight 1 1 minus 1, and weight 1 2 minus 1. So these two should be minus 1. Oh, well, actually, the thing here is they are classifying this as positive and this as negative. I proposed the opposite, these first two as negative and this as positive. So what they mean is that this is a solution again, and I mentioned this many times before. There are multiple solutions to this. There's no one better than other unless we apply certain rules or criteria for test them. In this case, they don't give that, so we're good with our solution. What's next? Can Adeline network be designed? Oh, okay. Now next we need to consider more categories. Um, Canal network be designed to make such distinction 1 1, 1 minus 1. Okay, we need to see them graphically. Okay, quick reply. You tell me, leave a comment. I am going to drink some water, and you have like 10 seconds to tell me if Adeline can do this. Yeah, ready? How reply? Think so. No, come on, Malik. We talked about this. The input vectors not to be distinguished are shown in this. These vectors are not lineable separable. So Adeline network cannot distinguish between them. We talked about this limitation these networks have. We cannot resolve problems that are not linear separable. What does that mean if that's not clear? And I need to be clear in that. I'm sorry. Need it means that one single function, continuous, linear, needs to be able to split the values and then that had the ability to classify it. Again, if we draw a line here, for example, in the middle, you can say, okay, whatever it's up the line, it's going to be one category, and whatever it's above that line, or sorry, under the line, it's going to be the other category. Sorry. The problem here is that with just one line, we cannot distinguish between these three values, because if we draw it here or here or here or here or here, or the point is that you cannot draw just a line here and say what it's on one side on or the other, classify these three. We could classify one and three, we could classify three and two, but not the whole set of them. So uh, since that, then we cannot resolve this unless, at least, sorry, with outline. There are other neural networks that are able to resolve not separable, not linear separable problems. One of them, for example, the multi multi-layer perceptron, not perceptron indeed, but multi-layer perceptron. And there's a technique for that. Actually, not that natively it's able to do it, but we apply a technique for that. Um, and yeah, so let's continue with another exercise because we're running out of time, and then we can finish for the session. And I will see you in the mini event, and that will be all for me in this Global Hack Week. And I will see you in the next one, the Beginners Week, right? I don't know if they already published it, but you have the premise with me. Suppose that we have the following input target pairs. These patterns occur with equivalent probability, and they are used to train outline networks with no bias. Wink. What does the mean square error performance surface look like? Oh, this is something I haven't applied to my code yet. The this graph. Oh, that would be a nice thing to have, but I don't think we should have enough time for doing this. I I owe you this, and for the next time, I will improve the code to have this. Sorry. Consider the system of problem P3 again. Okay, train the network using the LMS algorithm with initial guess at zero and learning rate at this value. Apply each reference pattern only once during training. Draw the decision boundary at each stage. Assume the input vector is p, it's presented first, the output and error are calculated as follows. The decision boundary associated with these weights is shown in the left, now applying the second input vector. Okay, this is one more for representing how the evolution of the process is, but I think we already have that like in mind, right? Now consider the converge of the system of problem P3 and P4. It's the maximum stable learning rate algorithm. Um, okay, this one can be interesting since here we calculate the eigenvalues. And remember, we made this, or we can do it with the MATLAB built-in function eigen, passing the formula or of sorry the value of r. The problem here will be calculating r, the diagonal terms of the matrix. It's giving the eigenvalues 101, yeah, while the columns, okay, again, more for understanding these, how to calculate delta. Um, so then, no other interesting example or exercise for us. The pilot taking, okay, this is more complicated. Is a classification problem that describes problems in P43 and 45, except that here we'll use outline networks. Okay, yeah, I like this. And the LMS learning rule rather than the perceptron learning rule. First, will we describe the problem? Nice. So, this will be very similar to what we made here. for the perceptron. No, sorry, here for the perceptron, and we will have four classes. We have a classification problem with four classes of the input vector of the four case. Train the Adeline network to solve this problem using LMS learning rule. Assume that each pattern occurs with a probability of one uh, 1/8. It's being displaying the input vectors as in figure P10, like circles indicates class 1, class 2 for these ones, class 3 for the rest, and class 4 for this. We will use the target vectors similar to the ones we introduced in problem 4P43, except that we will replace any targets of 0 by targets of -1. The perceptron could only input 0 or 1. Again, weak, because if we change the training, the transfer function, sorry, for Harlim symmetrical, then in the perception um, could output 1 and -1. Uh, but yeah, just I'll wink on that. Thus, the training set will be this. Let's code that very quickly. I'm going to split screen like this just in order to see. Oh, oh, that's a problem. Okay. Better, I'm going to reduce this like this. Yeah, nice. So again, let's create a new. Don't worry, I will upload all of this here to the repo I share. This is going to be P10 what? P10.8 plus 1. It's going to be 1, 1, 1, 2. And T1, it's going to be -1, -1. Then class 2, it's going to be, no, this is P1, this is P2, this is target 1 and 2, class 2, okay, target I can leave it just as target 1, P1 and P2, okay, nice. This is going to be 3, P3, class 2 is P3 and P4. These are 2 -1. These are 2, 0. And T2, it's going to be -1, 1, right? Yeah. Class 3, it's going to be P5 and P6. And these are -1 and 2 and -2, 1. And the target 3, it's 1 -1. Nice. C4, it's P7 and 8, and -1 -1, -2 and -2. On the target, it's 1, 1. Nice. Only thing I'm missing, it's this. P3 and 4 and target 2. P5 and 6 and target 3. Oh, this is PT3, this is PT4, this is PT5, and this is PT6. Also, this is going to be PT7, PT8, this is P8 and P7, and target force 4, 4. Nice. Also, we begin the problem setting with the following image. Okay, now that we have this, we can make this bigger for the sake of everyone. Also with this. Initial weight and biases, I won't do this since the algorithm already take them as what I was going to say. Um, as random. Another thing I have to change, and this is important for this exercise, it's rand 1, comma, input size. Yeah, this is important for this specific one. Just let me check something. Let me check now here in the perception if yeah, no, I'll leave it with 0, don't worry. What else? Prototypes, PT1, PT2, PT3. Okay. PT4, PT5, PT6, PT7, and PT8. Blah blah blah. The second iteration. Okay, now matrix weights. In this case, yes, I'm sorry. This won't be able to deal with 1. Here we will have to take same number of neurons. So let's replace these with 3. Replace this one, 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 this one. Yeah, this one. That's all. And also here, let's add a s value equal 2, and this is going to be here. Yeah, because this needs to change. Force. Well. Let me test something. I'm going to put this as a comment. I'm going to delete this. I'm experimenting, of course. Just like that. It's going to be created as a one, but no, then it should be more. Okay, and they tell us with 0.25, if I remember well. Oh no, we don't have learning rate here. That was from another exercise. This is done by hand. Well, let's run it. Let's see what the bugging needs to be done. Okay, yeah, I was hoping kind of something like this. Um, this is because of the plotting, the plot functions here. Yeah, I changed this, but I didn't change it here. The problem is we don't have zeros here. This is one and one. This is one. This is minus one. And this is minus one, one, and this is one, one. Uh, this should be now minus one, minus one. Okay, let's try to do it now. Nice, but our delta isn't good. Um, bias. What's this for? Answer, answer. Oh, okay, yeah, I see classification. Um, okay, yeah, it needs to move the delta. We need to move the delta. Let's try another very small one to see how this behaves. Okay, interesting. This appears to be close to the solution. I reduce it a lot more. Okay, now this is not working. Maybe one here. Again, not working. Maybe one here. Oh no, I went too far. Um, Another thing is that I am seeing that one one minus one minus what colors I added? Red, green, magenta, yellow. Red's not being displayed, and that's for class one. Red, 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 red. Why could that happen? Maybe if I change this to be minus one, and this to be just simply one, one, or maybe I'm doing something wrong here with the training data because this is minus one, and this is one, one. No, okay, should be good. Okay, no, they weren't the problem. The problem is the yellow ones. Minus one, one, one minus one, 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 two, two, three, three, four, four. Okay, I'm reassigning this value. Yeah, I knew I was doing something wrong around this T1, T2, T3, T4. Yeah, sorry. Yeah, now this makes a lot of sense. Liked how it worked, liked how we changed this, how the performance of the algorithm resulted. And just in time, actually, because we are in time to move to our mini event of Gartic Phone. So, 7 minutes left, Alberto. Come on fast. Yeah, thank you a lot. Uh, you're right. So I'm happy we get the chance to see the result of the both classifications, some to resolve some exercises, and I hope you like this series of MATLAB neural network design. If you would like more like this, let me know. If you didn't enjoy it, if you thought they were like too complicated or that it's fair. I mean, I am open to receive all kinds of feedback. If you think it were like confusing, but because of my way to explain it, I could work on improving them. So this is a very interesting topic for me. I'm kind of starting to be very passionate about this. Again, I try to study more and more about this. So I just wanted to share this little piece of knowledge with you. So see you around for Beginners Week, and that's all. MATLAB means therefore in the. I thought sorry, I don't understand you. MATLAB means therefore in the means. What do you mean? Well, I'll try to discover that. You can tell me in the minivan, Malik. Don't worry. But yeah, it was a pleasure. Thank you a lot for joining, and see you later. Bye.